Good evening, everybody, and welcome to the November 2021 Sigma meeting. I'm deputising for Pete tonight because he's not very well, but I'd like to welcome you all, Sigma members, initially, and all our affiliated clubs, Highland, Aberdeen Astronomy Society, Caithness Astronomy Group, and North Romildy Astronomy Group to this meeting, and thank you very much for joining us, along with any first time and guest visitors. A warm welcome to this meeting. I'm being helped tonight, run the meeting by Mick, who's doing the technical stuff, along with Stuart. At the end of the talk, Chris will be doing a quick question, or a 10-minute question and answer session, and then after the 10-minute intermission, Stuart will, well, I'll be introducing membership photographs, and then Stuart will do space news, and Mick will run through some deep sky objects on the Murray sky at night, which I think will be very interesting. So that sounds very good. And then I'll finish the meeting with some club news. And then after the meeting, there will be a membership gathering as usual. The link for that will be going into the chat. So at the end of the meeting. So look out for that if you'd like to join us. What I just asked you to do, I think most people are quite familiar with the Zoom controls, but I'd like, if you've got any questions for Simon, our speaker tonight, I'd like you to put them into the Zoom Q&A rather than the chat. And also the chat will be disabled during Simon's talk, although the closed captions will be put on. So that's a few details about the meeting. So I'll just enable the closed caption. Hopefully that will work. Okay. Anyway, I'd like to start then this evening's meeting by introducing Simon Cuthbert from Glasgow. He's going to give us which I've looked through the slides actually, and it looks an absolutely fascinating talk on Mercury. And as I said earlier, there'll be a short Q&A at the end. So without further ado, I'll introduce Simon and ask him to share his screen, and we'll get on with things. Over to you, Simon.
Okay. So here we go. And okay. Everybody see that all right then?
Yes, that's absolutely perfect, Simon. And I'm hearing you loud and clear, so we'll hand over to you.
Okay, let's just I'll pop you in the corner over here. Okay, so good evening, everybody, and thanks very much for the invitation to present something about Mercury to you this evening. It would be nice to see you in person, but this will have to do for now, and I hope you'll forgive any loud detonations going on outside. I get a terrific view for free of all the firework displays living up on a hill looking over Glasgow here, but it seems appropriate at the moment that there are rockets going off all around me. Also, we're at a good time for Mercury, and I think it's visible low in the sky a little bit at the moment if you're lucky. And of course, just over a month ago, Bepi-Colombo got its first views of the planet Mercury that it's heading for, and it's even done a little bit of science in the region around Mercury that we've heard about in the last few days or so. And I think you'll hear a bit more about that later, although I'm not really, that's where I step off really, where that starts. My slightly enigmatic title, the reason for that will then hopefully become apparent before too long. Oops. I'll just put my laser pointer on. So I stole this off Facebook earlier on today. And so here we have a nice image of the moon with some earth shine on it, but down here in the center of the lower left half of the image is Mercury, just that tiny little dot in the sky there. So thanks to Mark Sharon, I don't know if he's watching tonight, this is from the Astronomy Scotland Facebook page, and that was a very timely picture, thank you very much. So there it is. It's hard to see. It's very near the sun, of course, and it only tends to be seen around sunset, or I suppose sunrise. So quite an enigmatic planet to watch. But it was known, apparently, from early records from some cuneiform tablets from not long after 700 BC from the Assyrians, who noticed the way that it sort of jumped about the sky relative to the sun. So they called it the jumping planet. And it became, associated with various deities in the pantheons of gods of various cultures in early historic times. So the Babylonians associated Mercury with Nabu. And then when that came into the sphere of influence of the Egyptians, they had Thoth down here at the bottom left here, and it became associated with scribes and wisdom and associated things in their culture. And then again, when the Greeks and the Egyptians came into each other's influence, the Greeks had Hermes with his staff, and an association also with medicine, which was picked up by the Romans when they kind of appropriated the Greek culture, the Hellenic culture, and they associated Hermes with Mercury, and they gave a name to one of the days of their week to it, Dies Mercurii, which has come into use in Italian and French, as well as mercredi in French, for example. When the Romans, in their long battles and contacts with the Nordic and Teutonic cultures, they tended to sort of appropriate other people's gods and give them, their own characteristics. So they associated Mercury with Wotan or Odin, from which we get, again, Odin's Day, Wednesday, or Onsdag in the Nordic languages, is the same day of the week. So in spite of its enigmatic appearance in the sky, it has quite a lot of associations with ancient cultures. And in more modern culture, I managed to find a reference to Mercury in early 20th century art by Giacomo Balla, who produced this image of Mercury. It's a very abstract image, but the dark spiral that you see here is supposed to be the tube of a telescope viewing the sun, and we see the sun here with Mercury passing across the face of the sun, and all the strange white lights and kaleidoscopic colors are internal reflections within the telescope tube. So this abstract picture makes a bit more sense when you understand that he was actually trying to look through a telescope. So it finds its way into art, but let's find my pointer here. So, but the early telescopic observations, not long before that, when telescopes started to become good enough to see such a tiny object, started to give us some more detail, or very much on the limits of observation and the power of the eye. But Schiaparelli in 1889 noticed that he seemed to be able to see a network of apparently linear lower albedo features, rather like the canals on Mars that were claimed not long after that. So darker features forming a kind of network across the surface. And from observations of those and the way that they moved, he proposed a synchronous rotation and orbital periods where one day equals 1 year. And certainly Mercury has a very slow rotation, and it has a very long day compared to Earth days. And also from this, he was able to say that the rotation axis of Mercury only has a very small tilt in relation to the plane of the ecliptic, or rather in relation to the plane of its orbit. And if we compare that with modern observations, then In fact, Mercury has a 3-to-2 orbit to spin coupling, and its ratio of day length to a year is 2-to-1. Now that might seem rather odd, but in fact it is explicable. But I'm not really an astronomer or an astrophysicist. I'm a humble geologist, so I'm not going to attempt to explain to you why that is, mainly because it would take me about half an hour. So but anyway, the main thing to notice from this is that it's every year on Mercury corresponds to 2 days. The orbit of Mercury also is highly elliptical compared to the other terrestrial planets. It's got the highest ellipticity of the terrestrial planets, at least at the moment. If you were actually a viewer on the surface of Mercury, if you could stand the heat, or in fact the cold in some places, then you'll sometimes, because of this relationship between day length and year length, notice that the sun actually reverses its path across the sky and starts going back the other way, which on Earth you would find very disturbing indeed, I imagine. And then if we move up to other science missions, or another science mission, then Mariner 10 was an early visitor in the early 70s to Venus and Mercury. This rather ungainly looking craft compared to what we have now, first of all, needed some very good protection from the nearby sun, so it had a protective sunshade. It had a couple of TV cameras for imaging, and in black and white, an ultraviolet spectrometer, because it's so close to the sun. It's advantageous for charged particle imaging or detection. It had an ultraviolet spectrometer for doing chemistry, both of the region around Mercury and its faint atmosphere or exosphere, and the surface itself. There's an antenna here, which was used partly to locate and detect little wobbles that might be related to changes in Mercury's gravity field, and plasma science, a package just here, and then a magnetometer, of course, out on a long arm here, so that it stays away from the interference from the electronics on the spacecraft. And so when these images came back, it looked very moon-like, and this must have been stunning at the time. But it noticed that it had a very heavily cratered surface, that, like the moon, there are large impact basins, or large circular basin features anyway. It was able to show that it, like the moon, it had dust-rich surface materials, or soil, sort of regolith or soil. It's generally very dark, actually, in spite of the images that you see and how bright it looks in our sky. This slightly pinkish looking thing in our sky is really dark, and it has a lot of dark areas on its surface. So it's got a very low albedo. And in many ways, it's less cratered than our own moon, which in other ways it resembles, which kind of implies, especially as it's so close to the sun, that the surface has had less time to accumulate craters, and therefore parts of its surface must be relatively young. On average, the surface must be relatively young compared to the moon. It does have an active magnetic field, which is interesting, because that implies that it has a molten iron or partially molten iron core to generate the geodynamo effect, like the Earth. And other observations suggest that it has a very large metallic core. In fact, probably the top of the core is only 200 or 300 kilometers below the surface, so it's got an enormous lump of metal iron in the middle of it. Also, it has no real atmosphere, unlike Mercury or Venus, unlike Venus or Mars and the Earth, of course. But it does have a very faint, thin zone where there are atomic and molecular species suspended above the planet, and which we call the exosphere. And there was a hint from that actually, in spite of its proximity to the sun, there is some water ice, or perhaps other ices, in the polar regions. If we come on to the main source of our current information, although Bepi-Colombo, of course, is in there and starting its work about now, then it was the messenger mission here, Mercury Surface Space Environment Geochemistry and Ranging. Is a bit of a mouthful, so messenger. And it was there for over 10 years, and the mission was extended quite a lot from its original plan, and was actually able to get in quite close to the surface of Mercury and make some really startling observations at times. Although a lot of its observations, because of the nature of its orbit, tended to focus on the northern hemisphere. So a lot of the information we have from the southern hemisphere is rather faint. But anyway, it had a dual imaging system, rather more advanced than the previous mission, the Mariner mission. And this is able to image surface features and measure albedo. And that's over here. And then there was a gamma ray and a neutron spectrometer, which is able to do remote chemistry of the surface, and also detect ice with the neutron spectrometer. It had an X-ray spectrometer, again, using the sun's X-rays and their interaction with surface materials to measure the chemistry of the surface, but also to measure X-ray fluxes in the vicinity of Mercury. And there's a magnetometer to measure magnetic field strength, and there was quite a lot of new information gathered about the structure of the magnetosphere. There's a laser altimeter, which was able to do quite high resolution topographic imaging or topographic modeling of the surface, but also to detect slight wobbles or librations of the planet as a whole. And by detecting up and down motions of the spacecraft, along with other information that would help with that, it was able to show whether the planet was giving more or less of a tug to the spacecraft, and therefore kind of map variations in the gravity field of the planet due to variations of the density of the rock material at or under the surface, rather like was done on the moon in the 1960s. Then there was an atmospheric and surface composition spectrometer, which is just tucked in here. And so it was able to measure vanishingly small amounts of gases, gaseous species in around Mercury, but also it was another way in which we could detect and look at the surface materials from a mineral point of view, to detect the various crystalline substances of which the surface soils and rocks were made. And then there were things for measuring energetic particles and related to the magnetosphere. We've had quite a lot of rather wonderful auroras, although I haven't seen them the last few nights. You may well have done. And the same kind of things will apply on Mercury to a lesser extent. And then there was radio tracking of the spacecraft, again, to detect wobbles and ups and downs, and it's very precisely its position relative to the planet, to know where it was, and therefore to be able to map, and again to detect the gravity field from its ups and downs relative to the surface. So that's the Messenger spacecraft, quite a sophisticated package of instruments. Okay, so we can't really do some science without having some tables, can we? And there's a couple here, and we'll have a look at some of the kind of vital statistics of Mercury and pick out some highlights of it compared to the Earth. So in terms of its orbital characteristics, it's because it's so much closer to the Sun, it's got a shorter orbit. So in Earth days, 88 compared with 365. These numbers here, most of these numbers here, are really just telling us that Mercury has a more elliptical orbit than the Earth here, with its perihelion and aphelion significantly different to each other in millions of kilometers, while the Earth's orbit, at least at present, is rather more circular. But then also Mercury's orbital plane is tilted relative to the Earth's and the plane of the ecliptic a little bit, which does give us, I think, some advantages in being able to view it being so close to the horizon. If we have a look at some, just covering up my table there, so I'm going to move you down to the bottom corner of my screen. Okay, so if we have a look at some other characteristics of the planet itself, its rotation period in Earth hours is much, much longer than the Earth's. And in red here, where I've got red tech or numbers, then that's got to do with our own moon. So a long, long day. It's actually very upright in its spin compared to the 23.5 degree tilt of the Earth. Its equatorial radius is clearly a lot smaller than the Earth and a bit bigger than the Moon. So it's a small planet. And its equatorial and polar radii are very slightly different to each other. So it is slightly flattened across the poles relative to the equator as a result of its spin over a long period and slightly ductile interior. Its mass in 10 to the 24 kilogram units obviously is considerably smaller than the Earth because of its smaller size, in spite of the fact that it's got a lot of very dense stuff in the middle. And in fact, if we compare the densities in kilograms per cubic meter, we can see that Mercury, if we take into account the compression due to gravity, is about the same density. It's slightly less dense than the Earth. But if you look at our moon, it's much denser than the moon. And this is because, in common with the Earth, Mercury has this big iron core in it. If we take into account or we remove the effect of compression on the density, then in fact Mercury becomes the densest planetary object in the solar system. And then and that again is compositional. It's because of the amount of metallic iron in the middle. But because of its small size, the surface gravity is a lot less than the Earth's. And if we just skip down to the escape velocity as a result of that, you need to give something a lot less of an oomph to escape the surface than you do on the Earth, and that will become relevant to us a bit later on. So this thing here, the moment of inertia factor, tells us a lot of information about the distribution of mass in the interior of the planet. Generally speaking, the more this number approaches about 0.4, the more uniform the material in the middle is in its distribution. And we see that actually it approaches 0.4 more than the Earth does. But the moon here is much closer there. But that's because it's closer than 0.4 than the Earth, it's telling us that actually quite a lot of the interior of the moon is the same. And that's because the core is very, very big, whereas the moon's value is very high because it has a very small core and the rest of the material is less dense. The strength of the magnetic field, which is what this thing here is orders of magnitude less than the Earth's, but it does have an active geodynamo. Its magnetic field is a lot less tilted than the Earth's. It's almost upright, but not quite, relative to the polar rotation. One very important thing is that its proximity to the sun means that it has a huge thermal energy input compared with the surface of the Earth. And that might be important because volatile materials will tend to be volatilized and removed from the surface quite easily. And that led to some ideas early on, and also its proximity to the sun, perhaps when it formed as a planet, that it would lack volatiles, but it turns out that that's far from the truth, as we'll explore a bit later on. So we can say that Mercury has seasons, but due to the eccentricity of its orbit rather than its tilt, its orbital plane is inclined to the Earth's. It has locally very extreme surface isolation because of the day to year ratio, and the fact that at some times when it gets close to the sun, it gets heated locally a lot, so we get these hot poles. And it does have a very large dense body within it, because of the bulk density suggests that the bulk density is much higher than the density of the rocks at the surface. So there must be something even denser in the middle. And the magnetic field suggests that it's iron. The escape velocity suggests that it can release material from the surface easily. It's got an active geodynamo, as I said, and the surface temperature varies a lot, from only 100 kelvins up to 700, which is about -173 up to +426 Celsius. So on the one hand, we may get ices in the polar regions, but on the other hand, we get up to the sorts of temperatures in which any volatile material is like to be lost from the surface. So if we take some of that information and and some geochemistry and try to model the interior of Mercury compared to with information and lessons from other planets, we can see that it has a great big solid iron core, a liquid outer core, which will generate the magnetic field. And then geochemical modeling suggests that it will have actually a layer of iron sulfide, probably something like troilite, like you find in meteorites, or related to pyrite, fool's gold, and a thin layer a few tens of kilometers thick around the outside of the core, where a lot of sulfur will be sequestered. And then we have a rocky, thin mantle, which is unusually poor in iron compared to the mantles of the other terrestrial planets like Earth or Mars. And then a crust, which is fairly thick, but relatively poor in iron, and that really derives mostly from surface chemistry observations. So a kind of a concentrically layered onion-like structure, which is very familiar from the other planets. If we have a look at some surface features here, this Mercury, like I said, is very dark, but if we stretch the contrast a lot on the image, we can start to see features on it. And some characteristic features of the surface of Mercury will be areas like the big pale patch, a big impact basin, probably Caloris planitia, or the Caloris basin, has quite high reflectance and a reddish kind of tinge to it. It's also fairly flat and not too heavily cratered compared with other areas. But likewise, there are also plains which are very dark and have a slightly bluish tinge. And we also find the dark material in kind of halos or aureoles around some of the big impact basins, like over here on the right limb. And we also have these streaks that radiate out from some presumably quite young impact craters, and these are ejector blankets or ejector rays, which would be mixtures of rock and dust particles and probably melt glass. And characteristic forms that are very common, as on the moon, for example, are these craters with peaks in the middle forming a ring, or perhaps an individual peak if they're a bit smaller. If we have a look at some, we really enhance the colors. These aren't real colors, but they're kind of enhanced to show up features. Then we can see some of these surface features. And if we spin the planet around, we can see things like these pale basins as Caloris, again, these dark aureoles, the dark blue areas of low reflectance, and these, let's just, and then all these huge crater rays, some of them spreading almost half the way around the planet from these younger impact craters here. And like on the moon, they look pale colored because they haven't had time to be what's called space weathered, and solar ionizing radiation or ionizing particles tends to kind of darken the surface over time. So that shows that these are relatively young features, which we can also see because of the way that they cover over things that they cross, and so they're superimposed. If we have a look at the surface elevation from, say, the laser altimetry imaging, we can see that these brown areas are rather high. You know, they might resemble the Earth's continents, although in fact geologically they're not the same, or they don't have the same origin, we think. And then we've got the huge parts of the planet are kind of median and rather flat and not particularly rugged, these plains. And then we have low-lying areas, which are often circular or clusters of circles, which appear to be where Mercury has been excavated by major impacts. And if we take a polar view of that, we can see, again, these big circular structures. There's Caloris. This is looking down on the North Pole, so we can see Caloris. You'll also see that a lot of the names used on Mercury are named after musicians and artists. So that tends to be the protocol that's been used here. So we have Goethe, Rubens, and Raditladi, Rachmaninoff, Rodin, and so on and so on. Wren, Christopher Wren there, Vivaldi. But we do see here that the Mercury's surface is dominated by large impact structures and lots of small craters. If we look at the gravity mapping, which is fuzzy in the southern hemisphere, but more highly resolved in the northern hemisphere, we see that there's a lot of variation in the gravity field due to variations of the shallow interior of the planet. And from these data and the altimetry data in the lower half of the slide here, we can actually try to work out the thickness of the crust of Mercury. And we see that there's a sort of belt of relatively thick crust around the equatorial region of the planet here. And often that thicker crust corresponds to areas which are very intensely cratered. So they seem to be very old features of the planet. And they correspond to high surface topography, excuse me, which is similar to what you see on Earth, where anything that stands up high must have a root underneath it, a bit like an iceberg, or like the Himalayas with their deep crustal root. And if we use the gravity mapping, we can also detect where there are concentrations of very massive material in the interior. And so this is Caloris again, and it's got quite a high gravity field in the middle. And the reason for that is that the low density crust has simply been excavated by an impact and displaced around it or into space. And that has sort of exposed the dense rocks in the interior of the planet underneath, or got them very close to the surface. So the average density of the upper part of the planet here is a lot higher than it is here, where you've got more low density crustal rocks, and so we get a gravity high. This was observed on the moon, of course, corresponding to the big impact basins, and at the time they coined the term mass cons, or mass concentrations, to explain them, and the same applies here. So if we start having a look at the features of some impact basins which have been less degraded than Caloris by subsequent impacts, there's a very nice one here, Rachmaninoff, where we see a circular basin with an interior ring of peaks here, which are formed by the rebound of the crust after the impact. And large impact craters or basins tend to have rings, and small ones like this one here don't tend to have a ring. They tend to have a peak or a cluster of peaks in the middle. And we also see this terracing around the edge, where the steep slope that was formed by the impactor collapsed into the middle of the basin. So we get these kind of landslip terraces forming there. There's Caloris, which must be quite an old feature, although not old enough to have accumulated as many craters as its surroundings. It's obviously made of a different material than the darker surroundings, a different soil or rock type. It's rather smooth, so it appears to have been paved over with something after the impact. If we have a look at, let's just get my cursor back, a flyover, we'll pick up a few features as we go past. So here's a crater with a big scarp across the middle of it. So that's a big fault running across there, and it's a little kind of scarp or mountain range across the middle of it here. And we maybe see a signal of that down here too. Get your eye into the fact that these are craters and not blisters. And so that's the floor of the crater, and that's a shadowed wall there. And there are peaks in the middle. And this is very rugged, old terrain. And if we start to move over, at the moment, a lot of the terrain is reddish, but it's becoming bluer. And we can see a crater with a little cluster of peaks in the middle there. It's starting to get a bit bluer, so we're getting some darker and bluish tinted material here. So the surface composition is changing. This isn't just because of illumination, it's actually different soil materials. Here we have another one of these fault systems, which is obviously post-dating the crater here because it cuts right across it. So there's been some tectonics going on. Here's an example of a crater that's hit the edge of an older crater and actually splashed some impact debris across to partially fill this crater here. So there's a sort of lobate front of the impact pile there. And then we move into a much smoother terrain here with a fairly young complex impact crater here with a beautiful terraced rim, and you can see this slightly radial structure outside of it, which is the impactite material that's been thrown out and spread out across the surrounding landscape here. And you notice that the peak in here is a different color, which again suggests that it's excavated down into deeper rocks, which have a different composition. And perhaps around some of these other craters, the blue aureoles around them are actually the same material that's been thrown out into the impact outside. In this case, that hasn't happened. But a younger, smoother surface would suggest that it's been paved over by something else. Without an atmosphere or any water, it's likely to be lava, flood lavas. Okay, and we'll just, you notice also that in this part of the terrain, it's the low albedo, but it's got these little patches and wisps of higher albedo pale blue material, which might be something different. It might actually be some quite volatile, perhaps sulfide material here. And the origin of that is of great interest. And here we have a crater, at least with a partial dark halo around it. So there's a bit of a flyover over some parts of Mercury, just to give you an idea of some of the things that we can see and look out for. Oops, let's just to quickly do a bit of a tour around some of the features. These are impact craters. This one is Brahms, and you see this beautiful radial structure of the impactite that's been thrown out. This will mostly be melt, which is solidified very rapidly into glass, probably full of rubble like breccia, and this very nice terraced rim that's collapsed into the hole made by the impactor, and a peak in the middle. And there's a close-up of the peak in the middle, and some of these peaks are hundreds of meters high. You know, there's substantial mountain ranges really. There's another peak here, and you can see here these very faint rays of dusty material that have been thrown out, and sometimes these extend hundreds of kilometers from the crater. And here's a central peak, which actually is forming a slight small ring, but you see the interior of it looks almost like it's been filled in by a lake. And these are probably later volcanics that have filled the impact basin all the way around. You see this smooth, less cratered surface here. And it's kind of flooded over and started filling in features in it. This is probably impact debris, and you can see the way that the lavas lap up against the edge of the debris pile there. And this kind of crackled surface, which is typical of a lot of these lavas. So that's a bit like the basalt lava fills in the Maria on the moon, for example. Around the edges, perched up above that level in a lot of the big craters, we find these localized little flat areas on terraces, which therefore are probably not lavas, but they're impact melt pools. Oops. There. And again, this is Radit Ladi here with its lovely ring of peaks here. Again, a substantial, almost alpine-sized mountain range here. And we see these circular fractures where it seems to have subsided in the middle like a cake that went wrong. If we zoom in on some areas of it, again, we see these flat areas, which would be impact melt pools. And we also see these troughs or rifts, which are faults in the surface, like a bit like a pie crust, really, where the lava has cooled and contracted and shrunk, pulling the surface open and forming these fractures and cracks. And then there's a lovely image here of some ejecta rays around a really young impact crater. So they're still very bright, high albedo features. Some craters, though, actually have these aureoles of very much darker material around them with a low albedo, so we have to explain that in terms of its composition. And in this very highly stretched and adapted color image, we again see that we seem to have some material around the outside of the crater, almost like it's bled out from the outside of it here. And sometimes we have this very high albedo material in the middle. So there's some kind of different rock or soil material here. It's quite common to find that craters have a flat floor, as I've shown before. And these flat floored craters with kind of not so rugged as their surroundings tend to be seen as lava flooded craters. The lava may come from outside and flowed into it, or it may have welled up from underneath. And here's a nice example of a partially filled, lava-filled crater. You can just see the ring of the central peak ring here that's been almost engulfed by lava. But then the lava has actually flowed through a gap down this channel and actually flooded into another older crater at a topographically lower level there. And you can almost imagine the way it's streamed through here. And in fact, this is called Angkor Vallis. And if we zoom in on this area here, that's the same crater. It's about 5 kilometers wide, and we get this idea of the lava streaming along the side of it and forming levees as it floods around the side of the crater. But it didn't actually fill it in and flood it because it was bypassing it. If we have a look at the polar region, the northern plains, we see outside the northern plains, it's very rugged and cratered. But within this area, we see these ghost craters, which have been almost completely engulfed by lava. And we see lots of these little hints of them here. So this whole region of many, many thousands of square kilometers has just been literally paved over with flood lavas after the formation of these craters. And in low lighting here, we see lots of sort of surface features of these things. We see these little wrinkles and folds in the surface here, for example. In some of the flooded craters, where they're deeper in the middle and around the outside, as the lava underneath has cooled, it's contracted, and that's let the surface sag down and stretch, and we get this kind of pie crust effect around it. We also see evidence of the surface wrinkling. So these things here are called wrinkle ridges in a huge lava plain. And these are because the lava is kind of subsiding towards the middle here, and so it wrinkles up in the middle. And there's a really nice one just down here. So again, these are substantial ranges of hills or mountains. They're quite big. They're literally folds in the surface of the lava. And they're just caused by the dynamics of the lava cooling and contracting and subsiding. So sometimes if the lava is kind of pinned at the outside of a feature, it will sag and stretch. But in other places where it sags, it literally flows into the middle and rumples up in the middle there. And then we get features which almost look tectonic, like this one, where we get radiating cracks or rifts. As it happens, just by coincidence, in fact, a crater has hit it almost right on the focus. But that was probably later than the cracks formed. And this is the sort of thing you might get if you had a buoyant mass of magma in the middle, which is pushing up underneath, and it's so buoyant and forceful that it actually cracks the surface around it. It's almost like the effect of pushing a sharp or a narrow, blunt object against a pane of glass or a sheet of plastic, for example. Occasionally, we have evidence of explosive volcanism, which is something, again, that's quite rare on, say, Mars, our moon, for example. And it implies that there's actually quite a lot of volatile material which would accumulate and then explode. So this is, it's up here on this image on the right here where it says pit. And this is called a facula. And it's near Rachmaninoff crater here. And if we got a close-up view of it by a close bypass, although it's a bit obscured at the edge of one of the image panels here, but you see this beautiful layered crater wall, and then the flat floor filled with actually very high albedo material. And a feature like this on Earth would be formed by an enormously explosive eruption and then the collapse of the crater into a magma chamber underneath it. And you see it's got this halo of bright material around the outside of it. And the geochemistry of this, which was managed to be measured because at the time that this image was taken, there was a lot of X-rays coming off a solar flare, which gave us lots of opportunity to measure chemistry. And it seems to be very depleted in volatiles, suggesting that it's lost those volatiles from the surface into space. So an explosive eruption. And it might have looked a bit like this. This is Io, one of Jupiter's moons, which is the most volcanically active body in the solar system. And we see this plume-like eruption that was actually caught by one of the Voyager missions here, an amazing coincidence. And we get this ballistic form because there's no atmosphere or wind patterns to disturb it, forming, coming down to the surface and forming a halo of actually quite sulfur-rich material here. And it's quite possible that the volatile story of Mercury has some similarities actually to Io. We might have something to learn from it and its volcanism. Volatiles may also be the cause of these rather weird patches or hollows here. So again, that's a shadowed rock face there, and that's a sunlit rock face there. And we have a terrain that almost looks like a corroded iron or rusted iron. Although some people, like on Mars, call them as Swiss cheese terrains. I'll just put my red pointer on. It's a bit more obvious to see. And we get lots of this around here. And it's almost like the surface is corroded or lost mass. And it may be that across this entire region here of kilometers wide, volatiles have been lost from the surface or the subsurface, and we just get this, the loss of material has left this rather corroded surface here. I'll come back to that in a little while. And so what about tectonics then? I'm coming to why I've called this the incredible shrinking planet. And we get these big long scarps, often slightly curved on Mercury, very characteristic features. There's one there, there's another one here, and they often cut across craters, so they must be younger than those craters. There it is going across there. And if we get a digital image, or a digital elevation model of that, we see the way that it cuts across the crater and forms this very large scarp here. You can see there's the scale in kilometers here, so they're hundreds of meters high, really mountain ranges, in fact. And there's another one going across there, and we've got a colored topographic image of it here. This is Endeavour Rupes and Antoniadi Dorsum just over here. So we tend to get a depression next to it where the ground is depressed down, probably by the weight of these upstanding rocky material here, rather like we do in front of big mountain ranges on Earth, like a fallen basin. And a geological explanation of these features is that the scarp is sitting on top of a thrust fault where there's a crack formed and the rocks here have been pushed up and over the rocks here. And of course, a structure like this implies that there's been shortening or compression of the crust. And that means that we must have something that's causing shortening of the crust. And the interesting thing is that you don't seem to be getting many other fault systems suggesting that elsewhere to balance it, the crust is being extended or stretched. And if you try and add up the total effect of all of these contraction features, it seems to suggest that the total crust of Mercury has been contracting or has contracted by up to 7 kilometers. Now, of course, the obvious explanation of that is that it's a planet that's cooling over time, over the last 4.5 billion years. And it's simply shrinking because it's cooling. Another possibility is that in its early period, when it was spinning faster, it caused a big early tidal bulge. And as its spin is slowed down, that tidal bulge has got less, and therefore there's been contraction. But actually, they're not just related to the equatorial region of Mercury. We find them all over the place. So it's an all over thing. Well, in fact, contracting planets or contracting Earth was a big thing to explain mountain ranges in the 19th and early 20th century, acting a bit like a shrinking apple, wrinkling the surface. And if we have a look at an image of the Earth focused on the Himalaya, and of course the other mountain ranges to its north, and off into the Caucasus and Balkan and Alpine system over here, these were explained by some 19th century geologists as due to shrinkage of the Earth. But of course, now we understand that this is caused by plate tectonics and convection of the Earth's interior. And we have as many places where the Earth is contracting, like the Himalayas, as we do where the Earth is extending, for example, along the mid-ocean ridges, and they balance each other out. But on Mercury, we don't have that kind of thing. And it seems that, and the contractions are a lot less than on Earth. So it seems that on Mercury, it is a shrinking planet, and these tectonic features are caused by shrinkage due to cooling and contraction. Very quickly, as a geologist, I can show you that it is possible to make geological maps of other planets. And this is a geological or partial geological map of Mercury. And the colors represent either the different ages of the rocks, and you can tell them by the way that different sorts of terrains appear to overprint or lap up against others, as I was showing you with the lavas just a little while ago. And they also may represent types of terrain related to processes like cratering and impact ejector blankets like here, basin fills like here, or lava plains like here. So they're to do with material, and to some extent they're to do with processes. And if we use our capability to kind of work out chronologies from the way that things cover and overlap and cross-cut each other, then we can make a stab at having a kind of geological stratigraphic system for Mercury, like we have for the Moon, the Mars, Venus, and of course the Earth. And we're familiar with the geological periods on the Earth. And in Mercury, we can do that as well. And the old, most rugged terrains here would be pre-Tolstoyan. The Calorian would be to do with around the time of the Calorian impact and its fill. Then we have a long period of not a lot happening and then another long period where we get a lot of the younger craters with their crater rays, a sort of equivalent to the Copernican system on the moon. If we watch the time here, but I've not far to go now. If we look at the surface composition from the geochemical measurements, it's very difficult to do absolute concentrations of elements, but we can have a look at the ratios of chemical elements. And the two of the most abundant chemical elements in rocky materials in the solar system and in meteorites too are magnesium and silicon. The magnesium silicon ratio can be mapped across the planet here. And we find that there are some areas where magnesium is depleted relative to silicon, and there are some areas where magnesium is enriched relative to silicon. And these sorts of places would be very similar to the most ancient and abundant lavas on Earth, the komatiites, or lavas that have formed in more recent Earth history called bornenites, named after an area in Japan, which are areas of extreme melting of the shallow Earth's mantle and eruption onto the surface here. If we look at aluminium and silicon, again, two very abundant elements in rocks, then we find that there are kind of mirror images of the magnesium situation. So we appear to have regions which are enriched in aluminium and depleted in magnesium. So perhaps these represent rocks that are more, not quite granite-like, but maybe like andesites, like the lavas that are erupting in the Andes and a lot of our ocean islands. Although the origin is probably not quite the same. But we also have areas like this where aluminium is depleted relative to silicon, and that's where the magnesium is high. Again, emphasizing that kind of primitive, very hot, early Earth-like lava systems. And if we look at a more volatile metal like potassium, it shows a big high in its abundance over the area of the Chloris Basin. So perhaps that basin has either excavated a region of higher potassium, or perhaps it's filled with a lava system that's higher in potassium. And that again fits the picture of low magnesium, high and relatively high silicon and aluminium. So potassium, aluminium and silicon, it gets to look a bit kind of granite-like, almost Earth-like in some ways. So we can begin to map compositional domains, which obviously must have some process related origin to them. So the rock types, to summarize, are frequently magnesium rich and iron and silicon poor, and interestingly very iron poor, and they resemble some primitive kinds of lavas on Earth. There are regional variations in magnesium and aluminium, and if you try to model these compositions in either in a laboratory or by chemical theory, then the sorts of compositions of the magnesium-rich ones can be generated by partial melting of a particular kind of meteorite called an enstatite chondrite, which it's thought was formed in a region kind of close to the sun in the early solar system dust cloud. The other thing is, what about these dark areas? So we have a darkish area here and a flyby over it where the altitude, we got down to sort of less than 100 kilometers below the surface, down to 50 or so. And during this low fly pass, the neutron spectrometer picked up over that dark region anomalously high counts of neutrons. And this appears to relate to the presence of carbon and probably graphite. So there's probably quite a lot of graphite in some of these regions. And it's been hypothesized that actually early in its evolution, Mercury actually had a graphite crust all the way around it. So it would have been absolutely as black as pitch. To form a graphite crust on a planet is a really bizarre thing compared with the models that we have for the other terrestrial planets. And of course, carbon is often related with volatiles, but if we have a look at this region opposite the Chloris Basin, the chaotic terrain, it was thought that that was created by a kind of lensing effect of the shock of creation of such an enormous impact basin. Kind of, if you like, plowing up or destroying the surface and reorganizing it, knocking it about. But in fact, if you have a look carefully at some of the features here, they look sort of corroded, but you still see impact basins compared with the rather smooth rims of impact basins in a region outside it. They've actually modeled the depths of these compared to the surrounding plains regions, and they're all lower. And the idea seems to be that you had a lot of volatile materials in here, probably rich in sulfur, for example, and maybe carbon compounds. They degassed catastrophically, perhaps because of some magma coming up from below, heating it up. And all that stuff just disappeared into outer space and actually lowered the surface here by up to 2.5 kilometers. And in fact, you can also pick out kind of linear features along here, which also look kind of corroded along them. And these may be fractures along which these volatiles escaped out into space and corroded and collapsed the terrain around them. So there appears to have been a layer under the surface which basically just turned into gas and boiled off, and the crust above it just collapsed into the hole underneath it like a collapsing cave. And up to 2.5 kilometers of crust seems to have been lost by this process. And then, of course, if we're interested in volatiles, we're interested in water, like we are, for example, on the moon. And there is some evidence of polar ice. So this is a map of solar insolation intensity. And it's clear that the deeper craters in the polar regions were very, very cold. And because there's no atmosphere to redistribute the heat, in spite of its proximity to the sun, these are extremely cold places, down to 150 kelvins temperature. If you look at say the radar image or some, then I think from radar observations from Earth, then all the red areas are permanently in shadow on here, and all of the yellow areas are radar bright, and that's an indication of water ice. So in the polar regions, you seem to have quite a lot of water ice here, and that may have been accumulated from lots of comet impacts or a little bit of water that may have been present and degassed out of the planet over time. And then Mercury has this exosphere, a sort of vanishingly thin zone, if you like, a bit like a thin atmosphere. But the chemical species in it are things like sodium, potassium, calcium, volatile metals, along with helium and hydrogen. This kind of image shows that here, that it's flaring off or spalling off material that appears to be sourced in the surface regions of the planet. And one explanation for that is that occasionally there's Mercury there in its orbit around the sun. It comes into a zone of micrometeorites that are being shed by an orbiting, I think a short period orbit comet. And when they hit the surface, they spall off the more volatile elements from the surface rocks and soils, and they actually are lost into the atmosphere because of the planet's relatively low escape velocity. And that gives us this exosphere of these metals here, in addition to the hydrogen and helium from the sun. I'm not going to talk about this in detail, partly because I'm over time, but I'm just going to say a little bit about it. And what this is really doing is saying that Mercury is very chemically reduced. It's not as oxidized as the planets in the outer parts of the terrestrial part of the solar system. And that has all sorts of bizarre effects, which we're still trying to understand. And basically, we're having to go back to the laboratory and to theory to try and work out what rock systems are like that are not like Earth, Mars, or Venus. And what you get out of it is that certain important chemical elements don't behave the same. Silicon doesn't tend to just form rocks and mantles. It has a greater tendency to go into the iron core. And we know, from a simple blast furnace that silicon will alloy with iron in a situation that's very reducing if there's a lot of carbon around. If we look at iron, it has less of a tendency to go into silicates. So we get iron poor rocks, and more of the iron went into the core of the planet, and that left magnesium relatively enriched, which is why we get these magnesium-rich lavas. Sulfur and carbon behave in bizarre ways. In the Earth, they tend to combine with metallic iron and generally go into the core, with a little bit left for us at the surface. There's a much greater tendency for silicon and carbon to stay in magmas and in rocks outside the core, and they may then separate out from those magmas as little droplets and rise to the surface to form a crust, which may explain why there's all this graphite on the surface, and why we have an unusual amount of sulfide in the soils at the surface. And Bepi-Colombo is going to tell us a lot about why we have these volatile materials. And when sulfides become oxidized by reactions with some types of rock near the surface, then they'll revert to being volatile and give off sulfur, carbon monoxide and things. And that may be what's the cause of these explosive eruptions. So it's the different behavior of chemical elements in Mercury's less oxygenated environment that may be explaining some of the differences that we see. And maybe that's because of the zone around the sun in the early solar nebula having been stripped of a lot of its oxygen and its silicates by the early solar wind, for example, and leaving the heavy metal particles behind in higher concentrations, giving a reducing and metal-rich atmosphere, a region in which Mercury formed. That's one explanation. Another explanation, though, of the way Mercury is at the moment is a bit like the Earth, a giant impactor model, which would have stripped off the outer rocky mantle and left the big core in it. And so it's a lot smaller than it was when it started, which is another reason that I've called this the incredible shrinking planet. And it shrunk catastrophically because the outside of it was basically knocked off. Or it may be a combination of both of these things. So if we finish by having a look at a kind of geochemical model for the evolution of Mercury, then we have the raw material, the enstatite chondrites, which accumulated and accreted together to build a planet, an early protoplanet. The iron separated out and rained down to form a core, leaving a rocky mantle and a magma ocean on the top. The sulfur tended to partition into the magma ocean, as did a lot of the iron. And interestingly, uranium, which is a nice radioactive heat source to keep the outer part hot. And then gradually the magma ocean crystallized and filled up with crystals, and eventually, and including a lot of carbon, which would have floated to the top to give an early graphite crust. And then subsequently, perhaps because of the heat from all the uranium, we had a secondary period of melting in the planet's interior. A lot more sulfur came up to the surface. Impacts were gardening and mixing up the graphite with the lavas that were erupted out over the top to give us the modern surface of the planet. So that's the picture that we have so far, but the future is with the new Bepi-Colombo mission, which is a joint mission basically of two spacecraft from the European and Japanese space agencies, just there, and we're looking forward to the results from that. So rather belatedly, I'm afraid, I will thank you very much for your attention.
Thank you very much for that, Simon. We'll hand over to Chris for a couple of questions now, and if you've got any further questions, please prop them in the Q&A. That would be great. So over to you, Chris.
Thanks, Rich. Yeah, Simon, thank you. That was awesome. Stunning photographs. Thank you very much. I'm loving the idea of messenger. How very apt for the mission. Although I can't help thinking that they came up with the word first and then spent a week trying to work out the acronym to go with it. But we've got a couple of questions. One's come through from Rich. Do we have any idea how big the crater walls are on the Rachmaninoff crater? It's the ones that collapsed a bit on the outer ring.
Yeah. Well, I can't remember. If I looked at the digital elevation models, it would give an idea of what they are, but they are hundreds to thousands of meters high. They're very large structures, definitely. Yeah.
Cool. We've got question from Keith and Angela Nicholson in Caithness. Could the loss of the volatiles contribute to the contraction of the crust and fault scarp formation?
I don't think so, because the loss of volatiles tends to be very localized. It's kind of patchy, and you don't tend to see a direct relationship with the fault scarp formation, I don't think. So the loss of volatiles is quite a superficial thing. It's the outer few hundred meters, whereas the scale of the fault scarps suggests that the faults themselves penetrated quite deep down into the crust. So so the volatiles create different kinds of geological structures, which are basically collapse pits. But I suppose if like on Earth, we're going to look at fault systems which acted as conduits for the motion of volatiles or even liquids like lavas to the surface, you'd expect to see volcano-like structures actually lined up along these features, which again is not something that you tend to see. And I'll just add to that to sort of extend the answer a little bit, that I think one of the people who's been working on this a lot and is one of the mission leaders who's going to be very excited at the moment is Dave Rothery at the Open University. He's pointed out that in a system of a crusting compression, it's actually very difficult to get volatiles and lavas, for example, out to the surface because the cracks are always in compression and being pressed together. So you need to have localized areas in tension occasionally in order to get the gases out from there. So again, fracture systems that are in compression don't tend to be ones through which volatiles can escape. But who knows? Let's watch out. We'll get a lot more resolution of the images and a lot more details soon. So perhaps we'll see a closer relationship between tectonics and volatile degassing.
There's three. Well, I have a question. There's two other questions coming in a similar sort of vein. And firstly, I'm obviously interested to read about the relationship between the Earth, between the day and the year, similar to Venus. And then the whole thought of a reversing sun. I struggled when the clocks go back by an hour, but to have a reversing sun, I think would just be too difficult. Yes. But there's a question. I know we've spent a lot of time sending rovers to Mars. Is there any scientific benefit in sending anything to Venus? It looks on the surface like it's just another moon, the surface of the moon. Would there be any benefit in doing it, or would it just be physically impossible?
There's a difference really between the temperatures in the polar region are relatively low, and there's going to be, I suppose, there's going to be a kind of Goldilocks zone between the very hot and the very cold regions where you could actually do something useful. I think some people have written about this. I think maybe Dave Rothery has written a book about Mercury a few years back. But then again, if I remember rightly, there is actually a mission out at the moment that's getting very close to the sun, looking at the sun's characteristics there, and it seems to be capable of tolerating enormous temperatures and very unpleasant conditions out there. The electronics seem to be surviving. So maybe it's possible to put spacecraft in regions like that. I mean, if you wanted to do it on Venus, you've got to put up with temperatures that can basically melt solder. There are going to be limits, but I wonder. Yeah, I mean, certainly, I think the Bepi-Colombo is going to try and get some parts of the orbits of the two craft very close to the surface, but to actually be down there and drilling and examining things in close detail does have enormous benefits, and it may be possible to do that in certain areas in what I call the Goldilocks zone. And also, it's often easier to deal with extremely low temperatures if you've got enough energy to keep things warm. If you've got heaters, dealing with very high temperatures is much more difficult because it's very hard to shed the heat from the craft. So it may be that working in some of the the more shaded places where it's extremely cold might be possible, as long as you could get some electrical energy in there to heat things up occasionally.
That sort of sorry.
Yeah, go on.
Oh, sorry. That sort of leads us on to the next couple of questions. Obviously, I know that Venus has a temperature and a pressure issue, but Bill Graham has asked, how does the temperature vary over Mercury day to day? And if we landed on the dark side, would illumination be similar to a full lunar darkness? And as a sort of supplementary, the next question is, would a manned visit be possible?
Okay, so you're stretching me out of the region of geology a bit, but I'll have a humble go at it. So on the dark side, because you have no atmosphere to scatter light through an atmosphere, I suppose a bit like the moon, the only illumination that you're going to get are from the stars and from say Earth shine or Venus shine from those planets. So it's going to be pretty dark, I think, even compared with Earth. What was I think the question disappeared off my screen at the moment. So
yeah, sorry, my apologies. Let me see if I can get it back up. But yeah, so would illumination be similar to the full lunar darkness, and then would a manned visit be possible?
Yeah, I suppose the only other thing is that you've got some reasonably bright planets sort of outboard of it that might give off a bit more light, like Earth and Venus. So it would be fascinating actually to look back on the Earth and Venus from the spacecraft and see what we look like from back there, from down there. But yes, it's going to be pretty dark, I think. So operating in darkness like that is difficult, I should imagine.
Okay. We have one more, so if anybody else has any questions they desperately want answered, then please, you've got about 2 or 3 minutes before Simon finishes. But the last one currently on the board is from John McNichol. Do you think a lander stroke rover could survive temperatures at the polar region if solar energy was at a low instant angle on the surface? I think we've sort of chatted about that a little bit with the Goldilocks zone, but if you have anything else to add on that.
It's a technological issue, really. So but like I say, it's probably easier to deal with a cold region than a hot one. So either you stay in what I call the Goldilocks zone, or if you want to go into extremely cold regions to stop embrittlement, for example, in extreme cold of your equipment, you probably need to have captured enough energy to have heaters in it to keep it warm and insulators. I think there has been some discussion of that kind of thing. I can't remember where I read it, but it's worth having a search around for that. And if I find anything, maybe I'll drop you an email.
Cool. Thank you very much.
If I remember where I saw it, yeah. So thanks for the question.
So yeah, if anybody else has any questions, if Simon's around for a little while longer, then we can pose those later on. There's plenty of comments in the chat. Excellent chat, and I'll hand back to Richard now. Thanks very much.
Okay.
Chris, thank you very much for that. That was a great job. And Simon, thank you very much. It was a fascinating and very detailed talk, and it was rather good to have a geologist perspective in a talk, because most of our speakers come from a space and physics sort of perspective. So it was a very interesting view to have, and a great talk, and thank you very, very much. We'd like to send you this glass to say thank you very much for entertaining us and enlightening us for the evening.
Lovely, thank you. Splendid. I shall make good use of it.
Yes, good man. Yes, they're rather fine.
Thank you, that's very kind.
So, not at all. So we'll contact you in the next couple of days and get your address anyway. So thank you very much for that. And we'll move on to the intermission and have a 10-minute break, and then we'll gather for members' photos, space news, and the Murray Sky at night, and some club news. So, but please continue to stay with us, Simon, unless you've got a pressing engagement.
Yeah. No, that's fine. Thank you.
Not at all. And well, thank you. And we'll get on. But that's great. Thank you very much. Okay, well, welcome back to the second half. What we've got happening in this section is we've got a members' photographs, and then we'll move on to Stuart with Space News and Mix Murray Sky at night, and then I've got a bit of club news for you all after that. So we'll move on to the members' photographs, and I'll just share my screen and we'll there we go. We've decided to call this section the Alan Tuff sections, and I'd like to thank Alan very much for sending us some absolutely superb aurora pictures. Again, we've got several images taken from locally from Hopeman on the Murrayford beach, and this first one again shows a great image with the vertical towers in it, and all the greens and the purples and pinks and that. So that's a really smashing photograph, Alan. And then this is a further photograph taken about 9 o'clock on September the 30th. So, and another one here. This one's taken from just by Elgin. So again, it's not impossible at all. You can see the bright lights of Elgin viewed there. Again, this one was taken in September on the 30th, and another one here on the 30th, taken a little later at 10 o'clock. That's a great image. I love the contrast between the clouds and the pinks or the pinks, purples, and then the green banding with the vertical arrays in it. That's fascinating and a really nice image. And then this one was taken last Saturday. So I know Pete and Stuart and myself gathered near Fochabers in the early evening to try and see what we could see. We were out about 10 o'clock, so it was a little before this photograph was taken, but again, another spectacular image. And finally, this one shows a shooting or a meteorite going right the way through the image. So that's not only is it a great image, it's a good bit of timing as well. It's again, we did a bit of observing on Saturday night, and we were quite surprised at the number of shooting stars we saw. There was, 2 or 3 an hour. So so that was great. So thank you very much, Alan. They're spectacular images, and I'll hand over to Stuart now. So over to you, Stuart, with some enlightening space news. Thank you.
Right, welcome everybody to Space News. As normal now, there's quite a lot going on, so it's difficult to say, well, what should I put into Space News? Otherwise, it would go on all night. But I picked up 1 or 2 issues and 1 or 2 items, which some you may have already seen, and I hope it's not too repetitive. Okay, looked at commercial and tourist space flights. Chinese mission fills key gaps in the solar system history. NASA's spacecraft to crash into an asteroid. Bepi-Colombo's first views of Mercury. This ties in with what Simon said, but I'll just be covering in the higher level of the spacecraft. Australia launches space weather satellite, and some general space events and updates. Russia launched its first, on the 4th of October, the first ever film crew to the International Space Station. Russian actress Yulia Peresild, film director and a veteran cosmonaut, and they made a 4-hour 2-orbit rendezvous to the space station. It took off on the Soyuz MS-19 spacecraft with a Soyuz 2.1 Alpha rocket. And it was actually decorated for the movie, but you can't actually see too much on there. And on board, you can see the three film star, director, and the cosmonaut on board. And their role was to go through the fictional plot, which was a Russian cosmonaut who suffers a cardiac arrest during a spacewalk at the ISS, and he needed emergency surgery in order to survive the trip back to Earth. And they now had a surgeon on board to actually sort that out. They returned back to Earth on October the 17th. And also, which you probably saw, Captain Kirk, or William Shatner, who played Captain Kirk in the original Star Trek TV series and films, blasted off on the 13th of October aboard Blue Origin's New Shepard spacecraft, and in conjunction with three other people, including Audrey Powers, who is the Vice President of Mission and Flight Operations. He's now the eldest person who's been into space at the age of 90. And that is him going aboard the Blue Origin's New Shepard spacecraft. Another one that was going to happen in May, Deadline, an online news site, reported that Tom Cruise was going to fly to the ISS in October for his new film, which is coordinating with NASA and SpaceX, and who neither of those have actually indicated what was going on. It didn't take place in October, but SpaceX is saying they've got a flight early in 2022 for a private flight for 4 people to fly around the Earth, and they think that may be the same flight that is Tom Cruise is going to use. Virgin Galactic is delaying the beginning of its commercial space tourism service to the fourth quarter of 2022, with the company announcing a reorganization of its development and test flight schedule. It will start this month, or should I say October, refurbishing and improving its spacecraft and carrier aircraft rather than fly its next spaceflight test. Unity 23 was due to take place in October. That will now be possibly mid-2022. And after the enhancement period and the flight of Unity 23, the next two, which is 24 and 25, which were planned for later this year, there's no public date for those flights. They found that after further inspection, there's 1 or 2 problems in terms of materials that they wanted to sort out before they continued their flying operations. They were also delayed, I think, which I mentioned last time, by the FAA, saying that they actually went out of their flight zone during the launch and they were grounded until that was cleared. The FAA cleared them of that anomaly, but they still decided that they wouldn't take the next October flight for Unity 23. Jeff Bezos has come up and said that his Blue Origin space tourism company will launch a commercial space station by the end of the decade. It's going to be called Orbital Reef, and the promotional material released by the company claims the station will be a mixed-use business park in space and will host up to 10 people. And the company will partner with Sierra Space and Boeing to build the outpost. They didn't give any indication of what it's going to cost, but Mr. Bezos has committed to spending $1 billion a year on Blue Origin, so I assume it's coming from there. But the announcement also comes at a time when NASA searches for proposals to replace the 20-year-old International Space Station. While funding has been agreed to the end of 2030 for it, Russia has said that they will probably withdraw in 2025 because of safety reasons, over fears of outdated equipment, which could trigger a major incident. But NASA announced plans earlier this year to award $400 million in private contracts to space companies to help the agency replacing the aging outpost. So I should imagine there'll be a lot more in the news on Jeff Bezos' activities on this space station. That's the future. Looking back, if you remember, Chang'e 5 returned from its trip to the moon on the 17th of December, bringing with it some 3.81 pounds of moon rock from a region called Oceanus Brachiarum, for which the scientists have been analysing. Tiny pieces of the newly returned rock have been dated. It's about 1.97 billion years old, give or take 50 million years. And that's a small piece of the rock that they've been working on. This gap, this closes a 2 billion year gap, which stretched from about 3 billion years ago, when most of the rocks in the returned Apollo samples formed, to about 1 billion years ago, when some young datable impact craters formed. Analysis of the moon rocks delivered to Earth by China's Chang'e 5 missions also confirmed that volcanism occurred later than previously known, but also deepens the mysteries surrounding that activity. They're not quite sure why it is there. But what this has done, they've been using the number of pot marks on the surface to age the area. And by having a sample and work out what the age is in the laboratory, they can work out the number of meteorite hits against that time scale. So what Apollo brought back, they are able to look at, that was older material, there's more holes. So their basis is that the more hits, the older it is, the less hits, the younger it is. They can then get an assessment of the age on the number of pot marks on the surface. They can then look at other areas and age that area by the number of pot marks, or other planets or other meteorites or asteroids, comets, or whatever that they see on the basis of the number of hits. So what they've found has provided a big increase in the understanding of aging of the surface of the moon. The results are described in a paper published on the 7th of October in the journal Science Daily. Further analysis is still going on to look at the volcanism that's occurred and why it's occurred in that particular area, as they weren't expecting it to be there. NASA has on the 23rd, I think it is, of November, is going to send a spacecraft to crash into an asteroid to move its direction. And this is called, the project is called DART, and it will test an asteroid defense plan called kinetic impactor technique, essentially shooting one or more large spacecraft into the path of an oncoming asteroid in order to change the space rock's motion. The target they're looking at is a binary asteroid, two space rocks moving in tandem, called Didymos, which consists of one larger asteroid measuring about 2,600 feet in diameter and a smaller moonlet measuring about 520 feet across. And that's what they're looking at. They're aiming at the smaller moonlet, and they'll fly at some tremendous speed into the moonlet. Although the spacecraft is small and the amount of movement will be very small, they believe that telescopes on Earth will be able to monitor the change in its orbit and therefore assess how much is needed to move any approaching rock. It is being monitored. I'll find the details of the monitor. few seconds. It's an Italian. It's monitored by a companion spacecraft operated by the Italian space agency called the Light Italian CubeSat for imaging asteroids, Lycia Cube. And it will attempt to fly nearby and get an up-close look at the action that takes place. NASA closely monitors all known near-Earth objects that could come within 1.3 astronomical units, 1.3 times the distance between Earth and the Sun. So far, the agency has detected more than 8,000 near-Earth asteroids with a diameter greater than 460 feet, which would be large enough to wipe out quite a big city, I should imagine. And just some points on Bepi-Colombo, which Simon mentioned. It was launched in 2018 on an Ariane rocket, a European and Japanese mission. Had its closest approach to Mercury on the 1st of October at an altitude of 199 kilometers from the planet's surface as it swooped past in a close gravity assist flyby. However, this occurred over the planet's night side when darkness precluded pictures, and the closest image from the flyby was taken at a distance of about 1,000 kilometers. And this is the first of 6 high-speed flybys to gradually set up the probe's trajectory for a critical maneuver in 2025 to enter the orbit around Mercury. And these are the flybys that it's going to do. You see, April 2020, it flew by Earth. And then as you work down, October 20, first Venus flyby, second Venus flyby in August 21, and then first Mercury flyby in October 21, which is the one that we've just seen. It's got another 1, 2, 3, 4, 5, 6 flybys before it gets into its orbit around Mercury. In fact, it's got another in June, another flyby of Mercury next June. More encounters with Mercury are scheduled 2023, 24, and 25, in culminating in the 5th of December 2025 to enter orbit around the planet. That's the artist's impression of the Bepi-Colombo, and I think that's the same as what, or similar to what Simon had. It consists of a European component called the Mercury Planetary Orbiter and an element called the Mercury Magnetospheric Orbiter supplied by the Japan Aerospace Exploration Agency. The orbiters are accompanied by the Mercury Transfer Module. The propulsion unit carries large solar arrays to generate power for the mission's ion thrusters, which help reshape Bepi-Colombo's orbit between planetary flybys. Shortly before Bepi-Colombo enters orbit around Mercury, the transfer module will jettison from the spacecraft stack, and the planetary orbiter will fire thrusters to break into orbit, then release the Japanese spacecraft to begin its own science missions. And so it will set up the Japanese spacecraft in its orbit, and it will then carry on and set up its own orbit. And there's a breakdown of what it looks like. The Mercury transfer module is at the back, and that drives it all the way to its close orbit when it's almost on its orbit close to Mercury. The planetary orbiter will then take the Mercury magnetospheric orbiter away with it, release it in orbit, and then carry on and set up its own orbit. It's going to take a little while before its orbit settles down, before it starts taking photographs. Photographs taken by the Mercury transfer module are black and white. What will come from the Mercury planetary orbiter will be colored photographs, which it can't take at the moment because of the impact of the other components of the spaceship stack. And that's the black and white that's been picture that was taken as it flew past. Now, Australia launches a weather satellite. Now, this is the first time Australia has actually launched a satellite, but it's been involved in satellites previously. And it's called the Cuava satellite, Cuava-1, and it's successfully deployed into orbit from the International Space Station. It was delivered by SpaceX on the 30th of August, having been launched on the 28th of August and waited for its launch. And a major focus of this shoebox-sized CubeSat is to study what radiation from the sun does to the Earth's atmosphere and electronic devices. And that's it being launched on the 30th from the space station. And that's it setting out on its orbit. And this is probably all know this is the Australian picture of what it's trying to protect against by monitoring the sun's waves that come from the sun and cause damage to flight equipment, power stations, and underwater cabling, as well as submarine communications and satellites. The idea is it'll be able to monitor the effect of what's coming from the sun and actually know when to take any action. You remember last time I showed the Astra rocket launch, which went sideways before it went up. They've now come up with a solution, or found a solution. The Astra and the US Federal Aviation Administration have investigated the anomaly, and on the 12th of October, they came up and said what the problem was. They identified a root cause, a problem with the propellant distribution system, 5 first stage of the 5th first stage engine. During the launch, the propellants leaked from the system, mixed and became trapped in an enclosed space between the interface between the rocket and the launcher. And these propellants were ignited by the engine exhaust, causing an overpressure event that severed the connection to the electronics that control the fuel pump, shutting down the engine less than 1 second after liftoff, which is why the rocket hovered until it could take off with only 4 engines producing thrust until the weight of the burnt off fuel had been disposed of. Another event, China launched its 40th mission of 2021 and delivered the Jilin-1 Geofen 02F remote sensing satellite into orbit. Its success brings China's rocket launch rate beyond the country's previous record of 39 set in 2018 and tied in 2020, according to Space News. So China is progressing very fast in terms of space launches. Now, I wonder if anyone can work out what that is before I show you. So look at the hole in the roof. The meteorite in Mrs. Hamilton's bed and the hole in the ceiling caused by it. That was a meteorite that crashed through the ceiling into the bed. Mrs. Hamilton apparently was asleep, and she heard this crash and jumped up. And when she looked behind her, she saw this lump on the pillow where her head had been. She wasn't quite sure what it was, reported it to the police, and the police came round, and they thought it may have come from a construction company nearby using explosives. So they went to investigate, and the construction company said it's nothing to do with us, but they did see a flash at night and bits breaking up in the sky. So they came back and came to the conclusion that it was a meteorite. And that's another close-up of the meteorite. It's not very often that happens, but there has been one previous example in Ann Hodges in Alabama, who was struck by a falling meteorite on the 30th of November in 1954. Like Mrs. Hamilton, Hodges was also asleep in her home when the meteorite came calling, but whereas Hamilton escaped her event unscathed, Hodges wasn't so lucky. And meteorites were about the size of, the one that hit Hodges was about the size of a softball and weighed about 8.5 pounds. And it struck her after rebounding off a radio console, causing a sizable bruise on her side. That one there is being investigated and analysed at the moment, and we'll probably come up with some more information on it. But it's quite interesting. I don't know whether Tim is online, whether he's got any more information on the meteorites. I'll be interested to find out. Solar flares. We saw the aurora. Now, what I'll try and do, if I can get it right, is show you what caused the aurora. This occurred between the 25th and 28th, and it was taken by NASA's Solar Dynamics Orbiter, and it's showing the close-up of views of the solar flares that occurred between those dates, which set up the aurora, and ending with a major X1 class solar storm. I'll let it run for a little while because it's quite impressive. You'll see a breakout at the bottom shortly on the Okay, so that's it. If anyone has any questions, I'll be happy to answer them.
Stuart, thank you very much for that. I'm always impressed with the amount of information that you managed to convey in your talks, and it's becoming, there's more and more to choose from, isn't there? It's quite a juggling act.
When I put it down and then something else comes out, I think, should I change it, put the latest version?
That video was really impressive. I thought that solar flare was going to leap out of the screen and at me. Anyway, thanks very much, mate. That's great. A great bit of space news, and we'll move over to Mick now. So thanks very much, and over to you, Mick.
Thanks, Rich. Thanks for that, Stuart. Brilliant. Okay, let's share my screen. Nope, not that one. Okay, you got that there, Mitch?
That's great, mate.
Okay. Super duper. I'll just get rid of it. Move things out of the way. Okay, good evening and welcome to the November 2021 edition of Sigma's Murray Sky at Night. So as usual, we'll have a look at the moon and planets, see what they're up to, and then we'll get going with some deep sky objects. As a wee change from the normal constellation tour this month, we're going to go off the beaten deep sky track. And afterwards, I've got a bit of interesting information to share about exoplanets. And then lastly, I'll let you know about this month's ISS, the International Space Station's time as usual. So I've set the stellarium here tonight for just before midnight. Orion, as you can see, has now risen. You can see the belt of Orion clearly, apart from the clouds, obviously, which seem to be hanging about permanently. I'll just put the constellation lines on for you. We can also see the long trail of Eridanus, which begins just here at Rigel, and yeah, that's to the west. High in the sky, we have the red giant Aldebaran in Taurus, and a little bit further, of course, we have the Pleiades. I'm moving this down because all my zoom controls are up the top here. But, and then further across, we have the head Pollux and Castor, and we have Cancer the crab, and we can just see the head of Leo the lion here coming up. That rises quite late at the minute. But that brings me to this month's special events, meteor showers. So there are 2 meteor showers in November, the Northern Taurids and the Leonids. I'll go forward to the 12th. To the 12th of the month. And so the Northern Taurids, which began in mid-October, reaches maximum, although only around 5 meters an hour, on the 12th of November, which is why I picked this date. The radiant will be from this area here. So if you go around like towards midnight, it's going to be nice and high in the sky. You should be able to see all the way around it and hopefully catch some meteors. Now, the moon's first quarter is on the 13th, so conditions are quite favourable for the Northern Taurids. Secondly, we have the Leonids. So moving down to Leo. The Leonids are famous for great meteor storms every 33 years, and we're now 22 years on from the last great display of 1999, although 1998 and 2000, so the year either side, were also excellent. However, they've only got a short period of activity from the 3rd of November through to the 2nd of December, with the maximum on the 17th and 18th. And if we go to the 18th, I think it's running, yeah, 4 a.m. So a bit, we'll be able to see Leo then is going to be quite high in the sky, so you're going to have good visibility all around to catch some of those meteors. And the radiant is just around Leo's head, so like the reverse question mark area there. You might not get a dazzling show, but they're swift meteors and they often produce pretty green trails. The peak is generally very narrow, so between 4 and 5 a.m, around about that time on the 18th, is going to be the peak. And this shower derives from Comet 55P Temple Tuttle. The only issue is that viewing is going to be compromised that evening by a full moon, or that night by a full moon, but we can expect around 15 meteors per hour. So moving on to talk about the planets. Mercury is a morning object at the start of the month, and that goes into superior conjunction on the 29th of November. Venus, after its eastern elongation on the 29th of October there, it's going to remain low in the southwest at sunset, a very bright magnitude of -4.6 to -4.8 through the month. Mars emerges into the morning sky in Libra in November, but it's low and it's tiny, so you're going to require patience until 2022 till we get a more favourable look at Mars. Jupiter is in Capricornus at magnitude minus 2.5 to minus 2.3. And so is Saturn, that's in Capricornus, just to the west of Jupiter at a magnitude of 0.6 to 0.7. Uranus came into opposition on the 4th of November in Aries, magnitude of 5.7. And Neptune is continuing its slow retrograde motion in Aquarius, a magnitude of plus 7.8. Let's go and have a look at some moon movements. So 1800. There we go. So some of the possible photo opportunities for some of you interested in. So 10th, 11th, the moon's going to be passing by Jupiter, continuing a similar vein. On the 13th, it's going to be just to the south, 1.5 degrees south of Neptune. So there's a pointer for Neptune if you want to have a look at it. It's going to be a magnitude 7.8. Then continuing through 17th, it's going to be just to the 1.5 degrees south of Uranus. And if we continue to follow the moon through the month, it will be passing by Aldebaran, 19th, 20th, and on the 23rd, I think I need to move my time a bit later in the night. It's going to be passing by Pollux. So that's the planets. Let's go and have a look at some DSOs, or deep space object, deep sky objects. I'll go back to tonight's view. 23, 50. So we're going to go, this month we're going to go off-road, as we call it, in the far northern sky to track down 7 tempting targets that often fly beneath the observer's radar. So our makeup consists of the urge to roam and explore new and unfamiliar territory. And for those deep sky enthusiasts, they love nothing better than going off-road to track down some lesser known targets. We're going to dig deep to some possibly unfamiliar yet some still inviting deep sky objects located in the far northern constellations of Camelopardalis, Cassiopeia and Perseus. Most of these are north circumpolar, that means they're never set from the UK, and they all culminate high in the sky, so placing them well away from the murk that you get near the horizon and providing you with some long observing windows. Perfect for any photography you want to do. I'm not going to lie though, because some of these targets might prove a little bit challenging, as you're going to find out. So let's start with the tiny planetary nebula IC 3568. What I'm going to do this month, I'm going to just use the power of stellarium to go and find it. So it lies just 8 degrees southeast of Polaris. It's marked down as being in Camelopardalis. As you can see here, it looks like it's actually closer to Ursa Minor. I'll put some labels on for you. However, if I zoom out a little bit, stick some boundary, the constellation boundaries on, you can see that it actually comes in the boundary of Camelopardalis. So this IC 3568, and zoom into it, is known as the, come on, it's up to the image. Oh, there we go. Oh, just as I pressed the zoom out button to start again. Right, I'll let, there we go. It's known as the Lemon Slice Nebula, which is a totally unsuitable nickname really, as it's far from yellow. It actually sports a pale green-blue colour, a bit like Uranus. But the Hubble Space Telescope's images were presented in a gaudy false colour, making it look like a slice of lemon you commonly find in a glass of gin and tonic. It's tiny, spanning a spherical 18 by 18 seconds, and it's relatively faint at a magnitude of 10.6, although it does boast a high surface brightness. Deep amateur images show a bright core surrounded by a small faint inner ring and a larger, more diffuse halo. Hubble's image obviously shows remarkably complex structure at the core. Visual observers need to battle a couple of disadvantages when tracking down the lemon slice. I mean, first of all, the position near Polaris makes it quite hard to look at, because you're going to have to point the telescope pretty much straight up from where we are. And its small form gives it a stellar-like appearance at low power, so you're going to need a telescope in the class of around 10 to 12 inches to provide the necessary magnification and resolution to get a good view of it. It can be tracked down through a smaller telescope, though, so no big worries there. On early evening in mid-November, it's going to be around 45 degrees above the northern horizon as night falls. So it's well available there. We're now going to head to the constellation of Cassiopeia, which is home to a great selection of bright open clusters. And IC10, a dwarf galaxy, is the second stop in our tour. I used to read them again. IC10. Its classification as a dwarf irregular galaxy, and it's also more importantly classed as a starburst galaxy, referencing the intense star formation that takes place there, the only one of its kind found in our local group of galaxies. It's easy to find, lying just 1.5 degrees east of Calf. I suppose if you imagine it as a W, the top right, far right star. It's 1.5 degrees above, and just zoom in there for you. Excuse me. Of course, being where it is right next to Cassiopeia, which lies slap bang in the middle of the winter Milky Way, that means interstellar dust and gas lying along its line of sight is going to heavily obscure your view. However, it still shines at a reasonable magnitude of 10.3, and it spans 5 by 4 minutes approximately, as seen in images. A 6-inch telescope can pick this up in a dark and transparent sky as a small, featureless patch of light, but a 12-inch telescope will show some granulation and no obvious nucleus. We stay in open cluster heaven of Cassiopeia for our next target, which just happens to be an open cluster and a huge one. Stock 2. So an open cluster is a star cluster made up of a few thousand stars that were formed from the same giant molecular cloud, and they have roughly the same age. More than 1,100 open clusters have been discovered within the Milky Way galaxy, and many more are thought to exist. Stock 2 is one of the better known open clusters amongst those that don't have a Messier or an NGC designation, and it's one of an amazing 100 or so open clusters known to live within Cassiopeia's boundaries. It's one of 24 open clusters that were compiled by the German astronomer Jürgen Stock in the 1950s, hence the name. You see its location, it's in southern Cassiopeia, close to the boundaries again, of Perseus, and let me just look at the boundaries on. So close to the boundaries of Perseus, which is here, and Camelopardalis. And it's 4.7 degrees southeast of magnitude 3.3 Epsilon Cassiopeia, which is this one here. This also lies in a rich Milky Way field, not making it easy again to pick out from the starry background. But measuring a whopping 1 degree in apparent diameter, it's best observed through a pair of 10 by 50 binoculars and at low power through a small telescope. Its integrated magnitude is a bright 4.4, but that's pretty meaningless because it's such an extended object. And its brightest stars shine at a 8th to 9th magnitude. So for our next star, we're going to head to Perseus. So find this fact, Perseus. I think that's centered. Excuse me. So Perseus is one of the great constellations of the late autumn sky. It's a haven for deep sky enthusiasts looking to get a bit of variety in observing, as it hosts some great open clusters and nebula, including the double cluster, the California and little dumbbell nebulas, and the famous Perseus cluster of galaxies known as Abell 426. Our last 4 tour stops lie within Perseus' boundaries, beginning with the off-beaten track galaxy NGC 1023. Find that. So it lies 5.6 degrees west-southwest of Algol. This star here, Beta Persei, which is the archetypal eclipsing binary variable star, which is close to the boundary of Andromeda and Triangulum. See there? And it shines at a magnitude of 9.2, making it the brightest galaxy in Perseus by quite some way. So NGC 1023 is a cigar or lens-shaped lenticular galaxy that covers 8.7 by 3.3 in apparent diameter. A 3-inch telescope is all you need to pick out its high surface brightness, and a 4 to 6-inch telescope should provide enough light to give a good view of its halo extending to around 3 by 1 minute. Next, in Perseus again, we have NGC 1491. So to find this one, find Mirfac, go down to Delta Persei, across to this one here, which is 43, I think. Sorry, Lambda Persei. Yeah, Lambda Persei. And if you go to the next star up and imagine a triangle with a peak over this side. I've lost it again. Let's get back to it. Here you'll find NGC 1491. So this is a fine emission nebula showing off a moderate surface brightness across its 9 by 6 minute size. This makes it a reasonable target on a good night for a 6-inch telescope, especially with the addition of a UHC filter and operating at low power. And as is the case for most nebula, it's only through imaging the nebula you can actually see the true majesty. It's a beautiful and colourful nebula of comprehensive and complex structure. And now the penultimate stop on tonight's tour, still in Perseus, NGC 1528, which is just a couple of degrees away from our previous target. Another couple to mention in Perseus, for those making a list, it's home to the Great Double Cluster and also M34, a grand open cluster, and they're both well worth looking into as well. This one here, NGC 1528, is one of the best second-rank open clusters in Perseus, is home to around 80 stars fainter than 7th magnitude. It's a bright and obvious open cluster. Let's zoom in on that to have a look. It's a bright and obvious open cluster when viewed through a pair of 10 by 50 binoculars. So you don't need a lot of equipment to have a look at some of these things. It's got a magnitude of 6.4 and spans 18 minutes in apparent diameter. It appears as a rich grouping through a small telescope with 30 or more cluster stars being easily picked out. That number rises to about 75 stars through a 6-inch telescope. For our final tour stop, we head to NGC 1579, known as the Trifid of the North. It's been named after its namesake, the Trifid Nebula, Messier 20 in Sagittarius. You can see it's located in the far southeast corner of Perseus. Let's zoom in a little bit. Oh, a bit too far though. Unlike Messier 20 that I just mentioned, the Trifid Nebula, the Trifid of the North here is both a reflection and emission nebula, although it's roughly half the size and it's fainter. The northern part is the reflection nebula component, and numerous sources suggest that a 10 to 12-inch telescope has enough light grasp to show it. The southern section is the emission nebula, and that's also catalogued as SH2-222. Deep amateur images show multiple lobes structured to the nebula similar to Messier 20, albeit on a smaller and less spectacular scale. So if you're going to go looking at it, try a UHC filter and see if that helps with your view. It's a prime target for imagers, and its high northern declination makes it well placed for long imaging runs on a good clear night. So that's the end of this month's tour. And before I mention the International Space Station, I've got a little snippet of information to tell you. Now, I'll just stop my screen share actually. Since Kepler was launched in 2009, most of you know, it was sent up to look for exoplanets. And more recently, it's been taken over by TESS, the Transiting Exoplanet Survey Satellite. And they've been looking for exoplanets within the Milky Way, within our galaxy. And so far, as of 1st of November, they've found 4,846 of them within 3,595 planetary systems. However, recently, as recent as the 25th of November, it's been announced that there are signs of the first planet outside our galaxy. And it's an M51, the Whirlpool Galaxy, which is some 28 million light years away. It's yet to be confirmed. His latest readings are showing it's about the size of Saturn, and I think what I read, it's about twice the distance as our Saturn is from our sun. But it's got an orbit of 70 years. Now, if you know how Kepler worked, it used transiting methods. So what it would do is look at a star, wait to see for a dip in the amount of light coming from the star, and then they would take it that there was a planet crossing the path. They would mark it down and make that an object to go and look at to confirm if it was whether or not it was a planet. But yeah, having an orbit of 70 years, going to have to wait quite a while. So it's been getting looked into this thing since October 2020 or September 2020. I only found out about it from a message from my brother who's down south. He's at Bristol, finishing off his PhD this year in astrophysics, and apparently they're all getting so excited about it. They're all going mad. So I haven't had time to put anything together for tonight, and it would take too long to try and explain it on top of what we've already done tonight. But if you search for exoplanets, if you're interested in it, if you go to the BBC website and just do an exoplanet search, and if you scroll down and look for the 25th of October, there's a page there explaining it, and there's a few links on that as well. You can also find it on NASA. I think NASA announced it as well on the press releases on the 25th of October, it seems to be. But what I'll do is I'll put a link at the end of my talk into the chat for a web page that you can go to. In fact, what I'll do, I'll just quickly share my screen again. For some reason, I'll share my screen again, and I'll copy this. Right, this is the BBC web page it's on. But if I go to this one, there's a whole paper. I'll give you the link to this page. And what you can do is if you go to this full text sources and using this little symbol, the left hand of the two that looks like the acrobat symbol, and click on that, you can download the whole the paper that explains what they've been doing and what's been going on. As I say, it was dated the September 2020. So they've been looking into this for quite a while before they've actually publicly announced it, although there were some things on the internet saying that it was a candidate, as it says in this paper here. But I will copy this link and I'll stick that in the chat right now, in fact, we're on here. For anybody who wants to have a look. Yeah, so that's about all I've got to say about that. Quite interesting. So the last thing, the International Space Station, this month it's a morning object up until the 7th of November, so a pre-dawn object, after which it won't be visible for us from here until the 22nd, and then it'll be an evening object right through to the 9th of December. So that's something to look out for. For those who don't know, as I say every month, for up-to-date timings and maps and all sorts of things, including the ISS, if you make a free account at heavens-above.com and put your location in, and that'll give you precise timings and star maps and all sorts of good stuff that you can find. So that's all for me this month. There's obviously more information in this month's newsletter. And if you want more information on Stellarium, I did make a video that's on the Sigma YouTube page to help you get started by finding your way around Stellarium. So that's me for this month. Rich, back over to you, Nick. Can't hear you. You're muted.
Can you hear me now?
Yep, got you.
Cool. I've got a bit of a problem with Zoom, I think. But anyway, hey, thanks, Mick. That was a great talk as usual, mate. Yeah, so lots of interesting things to see in our skies there. So thank you very much, mate. Hey, we'll just move on, and I put into the chat the link to the gathering with the meeting link and the meeting ID and passcode. So if you want to come along to that after I finish speaking, that would be great. And we'll look forward to seeing you. Just a couple of bits of club news, and the most important thing, and probably the most important bit of club news for the whole year, is the Christmas quiz. We're planning to run that again this year, using the same format as we did last year. So you know, that will be as a meeting with breakout rooms. I know Kevin's very busily working on all the questions as we speak, so thanks, Kevin, for that. And there's a couple of things though. We're going to run it like last year with breakout rooms, so that you can discuss the questions with your team. But because the restrictions have currently eased quite a bit, we were thinking that actually it would be possible for teams to meet physically together. So we just move my camera, that's better. So we hope that will be a little bit better, so and allow you to sort of physically gather together to answer your questions. So we do need, though, and this is absolutely imperative, Pete will be sending out a registration link in the next few days for the meeting. It's absolutely important that you complete that registration by Wednesday, the 1st of December. The meeting itself is on the 3rd of December. So, and we'd urge you not to leave it to the last minute to complete that. So, yeah. So if you have a quick think about who you'd like to join you in your team, and what we plan to do is we'd register you as a team. So what we need is the names of the people in the team and a team name. If you select somebody to register, that they use that name and the people in that team. Teams are restricted or are limited to 5 people. Again, we need registration by the 1st of December, though, for that. People send out the link with instructions in the next few days. So something to look forward to anyway, because I know the quiz last year went extremely well. So it's and as I say, we want to repeat that and hope to get a very enjoyable event going. Just a bit of news. The Sigma telescopes are still available for you to hire if you wish. There's a small charge, of £5 a month for hiring one of the 2 scopes. We'll use that fee to either repair any damage to the telescopes or get other ones so that more people can use them. It's and also, if that, we will obviously refund that money if the weather's been particularly bad that month. So it's yeah. So if you want to hire one of the telescopes, get in touch with Pete and we'll get one out to you. It's and finally, we're going to continue. Obviously, I think next month's meeting will be online. We will be trying to resume physical meetings as soon as possible, but we are just restricted by actually just how difficult it is to physically meet, and because we won't be able to use the tea rooms or the canteen facility there to make tea, and so it is rather difficult. But we obviously are though still observing observing things every Friday and Saturday if the weather permits. But we did most probably think though that we'd be returning to physical meetings in April, simply because it's very difficult to hold them if it's cold outside and we have to have the space ventilated. So anyway, but we are trying our best, I think. Okay, we'll and don't forget, all these meetings are available on YouTube. All the main monthly meetings are still available on YouTube, and the links are obviously in the newsletter. And it's a great way for you to catch up if you miss one of our meetings. So they're all available there on the Sigma YouTube page. So and also we'd urge you to invite your friends and family along to these meetings, to sort of try and to sort of spread the word and increase the club membership and everything. And don't forget, if you invite somebody along, their first meeting is free. So so don't forget, if you can, just invite a friend along. Okay, I'll just click the link and resend the. I'm having a lot of trouble getting my various bits of kit to work. I do not quite know what's wrong. It's anyway, that's got the meeting link sent again. That's put into chat, so that's got everything. We'll end this meeting now and put and we'll put up the final screen and close the meeting down and see you in the gathering. Okay, thank you very much for joining us this evening, and thanks to Simon for a really great talk, Stuart for his space news, and Mick for his Murray Sky at Night. Thanks both. Thanks all.